Okay, it's time to start. Today, this semester, spring semester, first seminar. I'm very happy to introduce the speaker, Professor Jaewon Song from KAIST, and he will talk about supersymmetric theory. Please.
Okay. Thank you very much. Can everybody hear me? All right. So thank you very much to have me here. It's a great pleasure to visit Quest and Sagang University and also see fellow friends here. So today I'm going to talk about some work that I've done with Sunjin Choi, with Kiat and Sok Kim from Seoul National University, and also probably I'll say a little bit about some ongoing work that I'm doing with Sunjin and my student Sinju. So the title of the talk is a supersymmetric model of information loss and recovery. That's a probably kind of grand title. I'm not claiming that I solved the information paradox problem. I hope I can convey you that you can actually use some techniques of supersymmetric field theory to model a particular aspects of this information problem and the possible mechanism for its recovery. And more technical title of my talk is actually supersymmetric spectral form factor and Euclidean black hole. That's actually the title of the paper. So to set the stage, let me start with motivation. As you know very well, there has been tremendous progress recently in understanding some aspects of quantum gravity, especially some of the groundbreaking work has been done by these people, including these people. There has been very interesting work about the computation of the so-called page curve from the so-called island formula that can possibly resolve the information paradox. And another related development is the computation of the so-called spectral form factor. And this has been worked out by these people. It's Cutler et al. It's 9-author paper. It also includes Shasashi and Santor. And this late time behavior of spectral form factor has classically some issue, and these people have shown that how that can be resolved if you do the analysis carefully. I'm going to talk about this a little in a moment. And one interesting aspect of these developments has to do with some understanding of the fine-grained quantity, such as entanglement entropy and energy level spacing, was somehow understandable by some kind of geometric formula. So one of the most famous example is this Euclidean formula, which computes entanglement entropy, and that's a fine-grained quantity. It's not a thermodynamic thing, but somehow miraculously, I think probably it's maybe not, but to me it's rather remarkable that it admits a very simple geometric reformulation in terms of like minimal surface area. That triggered lots of developments. And one of the big questions in this field is that why and how such formulae actually exist. Why do we have Euclidean formula? I mean, of course, there are derivations of Euclidean formula that I listed here, but some fundamental question is that, do we really need that? And why do we actually have this? And today, I'm not going to answer this question. I'm just posing the question. And I think this is one of some big mystery in this field. So today I'll be mostly focusing on this something called spectral form factor, which was this spectral form factor. I think it's for condensed matter physics or people work on like quantum chaos is a kind of classical thing, but it was proposed particularly by Maldacena and Papadonimas Raju that can be a good probe to test our understanding of information problem or what different formulation of information problem in quantum gravity. So spectral form factor is defined in a very simple formula. It's a analytic continuation of usual thermal partition function, z of beta, and you complexify beta by adding plus IT. Then since partition function is sum over Boltzmann factor, then if you take the z bar, then you get this form, e to the minus beta e plus e plus e prime plus minus it minus e prime, where we all know that the partition function is just sum over Boltzmann factor. And this quantity looks fairly trivial, but it actually can probe some fine-grained details of quantum system, because if you take t to be very large, it can act, so at very large t, it really depends on this energy level spacing. This small detail delta E will give you wild oscillations. So this is a one probe of measuring the discrete energy spectrum. If E is really continuum, then that factor will be washed away.
Excuse me. Partition function seems to be imagined complex.
Oh, so
Function.
the partition function, yeah, here the partition function z of beta itself is not complex, but here upon now I kind of complexify the inverse temperature like this, so that this really becomes that of e to the minus iht. So this is like a e to the time evolution.
Common partition function defined in Lorentzian and Euclidean, whatever, actually real, but that partition function is complex.
Oh, this is not the partition function, and I'm calling this as a spectral form factor. That measures the that can be computed once you know the usual thermal partition function.
G is a partition function.
Yes, z is a partition function, but this thing is not a partition function because there's an imaginary.
So
Yes.
temperature is a shift.
It's not temperature. It's more properly this is the time evolution, like this IHT.
Time evolution.
Yes.
So what if there is a continuous spectrum?
So when there's a continuous spectrum, there is a point where like E minus E prime will effectively vanish. So the wild oscillation will not. You don't actually see this oscillation in time t.
So it's crucial to have a discrete. spectrum.
Yes, exactly. So that's the hallmark, or the one of the most important reasons why we care about this.
Beta is actually the Euclidean power.
Yeah, well, beta is just usual just inverse temperature.
How that time. But I think.
I
It's actually the time. And the T particles.
Well, yeah, I'm not doing any Euclidean pathing table. This is just bona fide. This is 100% in Lorentzian, so I'm not doing Euclidean at all here. At least so far. Can I proceed? So another feature of this guy is that if you take t to be very large and take some kind of time average, then this rapidly oscillating factor will become trivial. So it becomes simply 1 because this rapidly oscillating thing phase will cancel out. So once you take the average, or using mathematical jargon, you're using the Riemann-Lebesgue theorem, this factor becomes 1. So at very large time, when you take the time average, then it essentially be class to E equals E prime, so that the spectral form factor becomes sum over e to the minus 2 beta, so that it's simply just partition function and twice of the inverse temperature. The actual value itself is not terribly important for my discussion, but the important thing is that this guy is not zero. So this does not decay to zero for a ordinary quantum mechanical system. So for a generic quantum system with a discrete spectrum, like one of the well-studied cases, the SYK model, like it has been computed to look like this. And the general structure is that so when this t is small, like at early time, there's a slope that things decrease exponentially, and it reaches the minimum, and then goes up. There's and this region is called ramp, and then it reaches a plateau. So this plateau is a region where your partition function becomes z twice of beta.
Is it still y-axis is the time average value or?
Oh, yes. So here, well, it's not really time average here.
The value is at given time.
So yeah, these are the value evaluated given time. And see that these red oscillating were are the things that evaluated for individual theories of SYK. Let me remind you that the SYK is defined as some kind of random ensemble average of quantum mechanical system, where this J is a not J. I didn't write here, but it's the coupling takes a random value, and if you pick one particular instance, then you get spectral form factor highly oscillating, which signals the discrete spectrum. Yes.
What is the
I'll get to that. So, and once you take the so-called ensemble average of the system, then it behaves as a relatively smooth curve of the ramp and plateau. The thing is that for individual theories, individual quantum mechanical model with fixed coupling, then it's widely oscillating, but roughly it goes up and the average stays constant. And if you take the ensemble average of the quantum mechanical system, then you see rather clean ramp and plateau structure. So
what is the shape of spectral form factor when the system is integral? So maybe flat to nature, similar. What happens?
oh yeah, so for an integrable model, I think that the plateau is rather generic. So but this is a typical behavior for actually chaotic system, which has where the energy level spacing is rather random. So for a generic quantum system or complex enough system, you expect this phenomena. But for for integrable model, you expect that the spectrum is rather I would say ordered in such a way that the level spacing is constant. Then that constant spacing will actually probably give you some periodic phenomena. I may be wrong, but so this is not necessarily true for a integrable model. But the integrable systems still sometimes has similar features. The plateau is rather generic. And one thing that is known in the literature is that the slope ramp plateau behavior is well described by a random matrix model, where people know how to solve. Now, so far I didn't talk anything about gravity, but now let's talk about gravity. As we all know, ADS-CFT correspondence, especially the ADS-CFT correspondence means that conformal field theory that lives in d space-time dimension is dual to some quantum gravity in one higher dimensional antidisturbed space. And the important thing is that this is an exact equivalence of non-gravitational system, this conformal field theory, and a gravitational system that lives in the bulk. So this is not an approximation, but it's supposed to be exact. Of course, that doesn't mean that you know how to compute it, but at least that's what we believe. In ADS-CFT correspondence, gravity works as a hologram of non-gravitational system that lives at on the boundary. So what things happens at the boundary is being reflected in the phenomena inside the bulk. And it gives a kind of, well, this is under a slogan that it's a precise quantitative description of quantum gravity, at least in anti-disturbed space. Quantum gravity is notoriously difficult to formulate, but in the context of ADS-CFT, if you believe ADS-CFT is true, then at least if you know the CFT, then at least in principle, you have a complete description of the gravitational system.
Is it now some new trend that to replace string theory by quantum gravity? It used to be string theory, now
Yeah, so that's actually a good point, that because the ADS-CFT, so ADS-CFT correspondence is originally derived in the context of string theory, of course. But the statement itself does not really depend on the detail of string theory. So the pressing question is that, is there any working example of ADS-CFT that goes beyond the framework of string theory? Is there a non-string theory example of ADS gravity that is dual to CFT? I think that's a very important question to be answered. But so far the working, well, I'm going to be agnostic about that. I have my personal belief, but
What is it?
that does not personally. I don't know. I mean, okay. What are my like one of me inside is telling me that I gotta be really die-hard string theory believer. Then every theory of quantum gravity has to be string theory. If you believe that string theory must be the ultimate theory of nature, then that should be the answer. But being much more modest or honest, then we don't really know. It'll be super cool to find at least one example, which is not string theory, but still implement ADS-CFT correspondence. Actually, if I'm allowed to derail a little bit, then there has been lots of attempts to get something like this away from string theory. One of the attempts is this famous work by Witten that he studied this like putative holographic dual for the pure gravity in 3 dimensions in anti-disturbed space. And his first claim was pretty remarkable because a dual CFT is described by this so quote unquote monster CFT. And Witten originally conjectured that maybe there you can find a family of theories that look like a monster CFT that might be dual to the pure Einstein gravity. And if that is the case, then through ADS-CFT correspondence, that's a complete UV complete description of quantum gravity, at least formally. But then later that was shown to be not possible actually. So that putative generalization of monster CFT was shown I think that the current consensus is that such theory do not exist. So the pure gravity does not have a good ADS-CFT description in that sense. Anyway, so yeah, that's a very important question. Anyway, so okay, one final thing. I guess everyone here should know that. Here probably already know that black hole in this bulk gravity comes from the thermal state from the boundary CFT perspective. Okay, now where's the information loss problem? So using ADS-CFT, one can compute the spectral form factor in the ADS bulk using ADS-CFT correspondence. And according to that computation, the dominant contribution to the spectral form factor comes from black hole. But then once you plug that in, then you get this decreasing function in time, and then it never comes back. So it exponentially decays. Once you just plug in your one-shell action for a black hole geometry, then you get this. But we know that spectral form factor should not decay even at very late time for a generic quantum system with a discrete spectrum. So at least we know that for a very late time, there has to be a plateau. So this shouldn't be the entire answer for the spectral form factor in gravity. But our classical, semi-classical gravity using ADS-CFT only gives us this, only the slope, without ramp or plateau.
So conformal field theory should have a discrete spectrum.
Yes. Right.
You have some example later.
Yeah, so in ADS-CFT, actually, conformal field theory is always put on a sphere. So we always,
Global radius.
yeah. So we have a discrete spectrum. So so there's an apparent mismatch between the two computations. So using the just quantum field theory or quantum mechanics computation, we are expecting something like this, but semi-classical gravity only gives us this. And that's what Malacena and Papadopoulos called as one version of information paradox. This is not exactly the information paradox coming from the evaporating black hole, but it's kind of related. And in recent developments, they have actually solved this problem by considering what's called a double cone or wormhole geometry. So in this very famous paper by Sasha and Sanford, they studied two-dimensional Jacobi Teitelbaum gravity in detail, and they worked out the Euclidean path integral for this to compute the spectral form factor. And what they have found is that there is a contribution that coming from what's called the double cone geometry in their term. This is actually Euclidean picture. And that gives you non-vanishing contribution to the spectrum form factor, which is responsible for this linear growth of the spectral form factor at late time. So once you add this wormhole contribution, not just a black hole, but if you add the space-time wormhole to your computation, then you get this ramp, so that that resolves the apparent paradox of the mismatch. Well, of course, it's not a complete resolution because they didn't actually answer about the plateau, but at least they have shown that spectral form factor in the JT gravity should not vanish at late time.
Sorry, where do you put that double cone geometry?
Oh,
yeah.
Yeah.
Where?
Yeah. So this double cone geometry is the one of the. It's not exactly a saddle, but this is a classical configuration in the bulk. So what they're doing is that you consider ADS gravity with two boundaries. So in the ADS Euclidean ADS, the boundaries are circle, and we have to compute ZZ bar. So I have one circle on the one side and the other circle on the other side. So to the leading order, the contribution comes from more like the disk-like geometry. So these are like two boundaries, and the leading contribution comes from the geometry of this form, and that gives you this decaying spectral form factor. And what these people have found is that there's an additional contribution that people have missed. That is this type of double cone geometry. That gives you an extra contribution, which gives you this factor.
Cone is not it's not important to be from the usual saddle point, right? I cannot understand why you said like it is different from the saddle point.
It's yeah, I'm not Well, usually, I'd like to add, like the contribution from the saddles, like this comes from one of the dominant saddles, and this is under saddle, and maybe this comes from under a different saddle, in the Euclidean pathing table. But for some reason, this is not exactly the classical saddle of that solves the, but still, this kind of geometry comes from some sort of zero mode. So this is a something like a zero mode contribution to the path integral. So slightly different from the usual like saddle point where you solve equation motion and plug that in. Yeah, I don't know very well. I don't know super precisely. So experts can correct
Stable
me.
configuration.
This?
Yeah.
I think that's what they believe. But what people believe, so that you can add. If this is unstable, then probably it's not good idea to add.
JT, in 2D JT gravity, is it stable or black hole solution is stable?
Yes, there is a stable black hole solution in two-dimensional.
Black hole in JT corresponds to a extreme limit of 4-dimensional
Mhm.
rise below the storm.
Mhm.
But in my understanding, in 4-dimensional are in black hole, so in the extreme limit, inner horizon will coincident with outer horizon.
Yes.
And as you know, inner horizon is unstable because strong cosmic censorship. So in this sense, JT gravity would be unstable, I think.
I think it's not really looking at that regime. It's here you get this effective action for JT gravity by studying the extremal black hole and just taking the near horizon limit and do the dimensional reduction. So the near horizon limit of the external black hole geometry has ADS2 factor, ADS2 times S2, and JT gravity is an effective theory that lives on the ADS2. So that's how you derive the action for the JT gravity. And here, assume that that is just given. Forget about the 4D origin. That might be relevant, but I don't know. But they are working in that region, that this JT gravity in ADS space is given, and try to solve that using Euclidean pathing. And that this is surprisingly doable, done by these people. And they have also shown that along the process, this JT gravity is dual, can be described in terms of dual quantum mechanical system, but the dual system is not a single quantum mechanical system, but it looks like some random ensemble average of some 1D quantum mechanical system. So this is actually very significant in this description, because in usual ADS-CFT, if I have two boundaries in space-time, then the partition function, so spectral form factor was simply Z bar. And there's no reason for this side of boundary to talk to this side of boundary. Fundamentally, from the CFT perspective, there's no reason for this region to interact with this. This is just a two decoupled CFTs. But suddenly, you create a bridge in the bulk description. This only makes sense if it involves some kind of ensemble average. Otherwise, partition function will simply factorize. So that was their interpretation. So once you take the ensemble average, then you get the ramp from geometry, which naturally explains this behavior of the spectral form factor. Okay, that's very beautiful work, but it's not a complete answer to the original question, because fundamentally we know that the ADS-CFT really works for one particular theory in the boundary and the one particular theory in the bulk. It's not about the ADCFT should work at the level of individual theories, not after taking the some ensemble average. So that's the puzzle. So can you account for this ramp? I mean, without taking some kind of ensemble average or wormhole, because this necessitates ensemble average. And the information has to be restored without ensemble average. So in order to attack that question, actually, before explaining this, there's also these people have tried to answer this question in from the point of view of like SYK model and J2 gravity. And personally, I find that to be a little what's a good word?
Not convincing.
It's not convincing. It's not pleasing enough. Let's say it's not clean enough to interpret. Is there a question?
I think it's just repeating your.
Oh. All right. So ideally, it would be desirable to compute spectral form factor for a more conventional ADS-CET cell.
Plus neutral.
Okay. So can we do that? For example, I mean, we know that for four-dimensional n equals 4 super Yang-Mills theory is exactly dual to type 2B superstring theory on ADS5 process 5. This is the very first example of ADS-CFT. And we hope to explain this the spectral form behavior of the spectrum form factor without invoking ensemble average. So in this setup, at least, the ramp should be accounted without any ensemble averaging nor space-time wormhole. But of course, there's a caveat that this, unlike the case of space-time wormhole, the resolution does not have to be geometric. So this is, if it happens to be the case, that would be great. Just like Ryutaka formula is so powerful and great. But yeah, maybe we may need some very nitty-gritty details of string theory or some UV complete description of quantum gravity to resolve this. Actually, that has been the traditional viewpoint of resolving many problems in quantum gravity. We probably need to know the quantum theory of gravity to actually answer all of this. But recent developments were actually trying to point the opposite. Maybe we don't really need to know everything to the Planck scale, because there are some good geometric formula that accounts for the details of the this aspect. So yeah, let's see if we can do that. But unfortunately, it's not. Even with this high degrees of supersymmetry, it is extremely difficult to compute spectral form factor. Nobody knows how to compute partition function of n equals 4 super Yang-Mills at finite temperature at strong coupling. That's impossible. That's mission impossible. Right. So to get away with that situation, we are going to use supersymmetric localization. The partition function itself is very difficult to compute, and I don't know how to do that. But there's a variation of the partition function. It's called superconformal index. That can be computed reliably at strong coupling. Okay, so let me just briefly review what the superconformal index is. It's a kind of close cousin to ordinary partition function, except that I insert -1 to the f. So usually, for the thermal partition function, I would not have this, but there's e to the minus beta, and I can add additional chemical potential. But once I add this -1 to the f, then it, of course, hugely underestimates the number of states. So I can roughly rewrite in the index has a property that it gets contribution only from the states that are annihilated by a particular supercharge. So this is contains much less information than the usual partition function. And it also suffers from heavy cancellation because of -1 GDF. It's a number of bosonic degrees of freedom minus number of bosonic states minus number of fermionic states. But schematically, it has this form. So just remembering that this omega is not the real number of microstates, but this is just a number of microstates graded by a fermion number. The pro is that this is calculable. That's a good thing. There aren't that many things that are calculable in quantum field theory, especially this is something that can compute exactly. But the bad thing is that only VPS states, supersymmetric states contribute, and it can only measure things at 0 temperature. This is strictly 0 because at finite temperature, supersymmetry is broken. So this only captures supersymmetric states at 0 temperature. So that's a bad thing because after all, we would like to know thermal property of a black hole, like black hole, like Hawking radiation, things like that. But surprisingly, in recent developments, people have found that this index, even though it looks like it hugely undercounts the number of states, it actually captures the microscopic entropy of supersymmetric black holes in ADS. And also, in addition to that, this index also has a remarkable feature of mimicking this finite temperature phase transition. So in ADS gravity, the generic feature of ADS gravity is that it has two distinct thermal phases. At low enough temperature, the free energy is dominated by gas of gravitons, but at high energy, the free energy is dominated by the large black hole. So once you heat up the system to very high temperature, then your gas of gravitons will collapse to form a black hole. In supersymmetric index, as a function of this chemical potential omega, it actually has a phase transition. So that's rather remarkable, and it's only recently, relatively recently discovered by these people.
How to understand the Hawking phase transition in the 0 temperature?
Oh, yes. Thank you for asking that question. So this is not, so there's a like. So it really mimics the phenomenon of Hawking phase transition in the sense that I can be more precise that instead of temperature, now it's a function of chemical potential. So so this chemical potential behaves like the inverse temperature. So when the chemical potential is large at low temperature limit, and in low temperature limit, the system looks like it's in the gauge theory description, it's in the confining phase. So there's your degrees of freedom is like the quark, not the quark, the baryons and mesons. There's 0.1 degrees of freedom, but at high temperature or small omega, then the basically degrees of freedom are the gauge theory is described in the confining phase. So you have n squared degrees of freedom. So degrees of freedom are captured by the gluons of the dual gauge theory. So that's very like the Hawking phase transition in the usual thermal sense. Okay. And that gives a hope that supersymmetry index may be relevant in this information problem, because the crucial thing is that it does know about the microstates of black hole. It has enough number of states to account for the black hole entropy. And the one historical remark is that this paper was written in 2003, I think. And these famous people have had this hope of finding entropy of black holes from the supersymmetric index, but they were not successful due to various technical reasons. But in rather recent years, in 2018, there are 3 independent groups have realized that it can actually capture the entropy of black hole. All right, so now using this supersymmetric index, let's compute the analog of spectral form factor from the index. So just mimicking that this G of P was partition function, complex partition function squared, we take the index and complexify that and take the absolute value squared. So here now I have written as tau because this is not really the time, because in the supersymmetric state does not actually evolve in time. But I have just introduced this funny quote unquote time. And what's nice is that even I can do the same kind of manipulation that just expand this in terms of omega and this way, like Boltzmann factor. Then it also exhibits similar behavior as the usual spectrum form factor at large tau. At large tau, there upon averaging over tau, this J minus J prime has to annihilate the phase, so that at late time, late quote unquote time, should behave like this. But this is a little bit too fast because the index has an unfortunate feature of being that it's periodic in the imaginary direction. So this is one one problem for the index version of the spectral form factor. So
이거는 차지 퀀타이제이션.
yes, exactly. Because the charge is quantized, so it should come back to itself after
그렇게 먹으려고 에버리지고 자고
So yeah, if I take this literally, then I cannot really pick a meaningful average. It's not long enough to see interesting behavior. It seems. But there's actually a way out. Instead of using the quote unquote canonical version of the spectral form factor, there's also something called microcanonical version of the spectral form factor. Instead of fixing the temperature or chemical potential, now we would like to fix the energy, or in this case, the charge. So I define this the spectral form factor in the following: that is the sum over microstate times. This is the analog of e to the minus iht, and I multiply that with the Gaussian factor, which gives you a window of the state. So I'm just trying to look at the states with some fixed charge. This minor is j, and this is j plus delta and j minus delta. Just I'm looking at some particular window with a fixed charge, and compute this. And the good thing is that this has a delta squared. This is an extra parameter that was not there in the canonical version. That gives you some good damping factor. So I choose this nicely, so that it can actually decay pretty fast. So we're going to study the spectral form factor around the charge n squared with a width of On, so that the most states contributing to this comes from the black hole, at least at early time. And we actually studied this because we are heavily influenced by this paper by Yimin Chen, who was about a Senate student. And he wrote a very nice paper studying the spectral form factor in the free Yang-Mills theory. So let me now quickly go over the evaluation of supersymmetric index. I should be quick because I'm running out of time. So for n equals 4 super Yang-Mills, the index takes the following form. There's -1 TdF, and these are various charges that n equals 4 super Yang-Mills theory has. There are 3 R charges coming from the SU4 R symmetry and 2 angular momentum. And these chemical potentials should satisfy this particular relation. This is due to that gives you the index. So this is a condition for this thing to be compatible with index. And index counts as the 116 BPS state satisfying this condition that the energy is given by the sum over these charges. And the index can be evaluated by integrating this complicated looking integral. And I'm not going to explain this in detail. If you're really curious, and please ask Junho, who knows much better than I do. And I'm only going to use the following. So I'm going to evaluate that this index in the large N limit. And that problem turns out to be a little technically complicated, but it can be done thanks to very nice work done by SNU group. That basically, upon some like clever manipulation, you can rewrite this the purchase function in terms of this 3-factor times some integral where it becomes trivial upon saddle point approximation. So the final answer is simply only becomes this. But it's technically very important to evaluate this precisely in a controlled way. In this, in the large N limit, this has a very nice set of saddle points where these people label as a parallelogram ansatz, and which solves which is stationary. Yeah, and that dominates the integral. So, well, yeah, I'm not going to explain this anyway. So, upon given that, once you evaluate that, your free energy or quote unquote free energy of the index is a log of z. For each saddle, you get this type of form. And the saddles are actually labeled by this number k and R1 and R2, and they are not free numbers. They have to satisfy some complicated looking conditions, because that solution has this is very important technically, but this is necessary in order to avoid various branch cuts and singularities. And in simplification limit of the 3 charges being the same, then I get this form. Now I need to sum over that to evaluate the partition function at large N. And the k equals 1 saddle turns out to account for the black hole entropy for the supersymmetric black holes in ADS5. And that's also called the quote unquote deconfining saddle, because the field theory dual of that describes the deconfining phase, or the high temperature quark gluon plasma phase. In a more fancy modern generalized symmetry language, in the deconfining phase, your one form symmetry is completely broken. But that's not the end of the story. There's also this k greater than 1 saddle. And these are non-perturbatively subdominant, because the partition function for this k cut saddle has an e to the s over k. So it's suppressed hugely by this factor. Also in generalized symmetric term, these saddles preserve some partial one form symmetry. Yeah, well, let me see. You can evaluate the black hole entropy from this one cut free energy by just applying Laplace transformation to this free energy and extremize that with respect to various chemical potentials and plugging that in. You get this very nice formula, and that agrees with Pekishian-Hawking entropy for this Kutoski-Rel type BPS black hole, which is super interesting.
Percentage is still index that, yeah, not,
Yes, this is actually index.
but it still matches.
Yes, it actually matches.
How?
Yeah, that's miraculous, isn't it?
I have one conceptual question. So in your original spectral form factor, because that form is the GG bar, so there is no reason for any that wormhole geometry. But in your generalized index version of spectral form factor, is it also same?
Right, it's the same. It has to be factorized. There's no ensemble average
No.
nor wormhole. So there's no reason for it to factorize. So, so what should happen? So what is going to happen? So just wait, wait for it. You can actually generalize this computation of large N index to more generic N equals 1 supersymmetric theories. But let me skip that in view of time. So upon this preliminary work, now let's look at the actual spectral form factor for N equals 4 supersymmetric theory, the supersymmetric version. So let me remind you that the psychokinetical spectral form factor takes this form. And the way to do this is that we can evaluate this omega by evaluating the index at the large N saddle point. And this omega can be computed by taking the inverse Laplace transformation, as we do in undergraduate setback. And then apply this in some with some Gaussian window. For large N, I can approximate this J tilde as some continuous integral over J tilde. And I can use saddle point approximation. So there's two different saddle point approximation, one for the evaluation of omega itself, but also for the evaluation of its y. So we are taking two saddle point approximations. And upon evaluating that, we get this form. So yeah, I have to sum over a variety of saddles labeled by K, R1, and R2, and evaluate this. Now everything else is just numerics. We don't have further analytic result, and this is what you get. So this is in the limit where the two chemical the angular momentums are the same. In this region, what we have found is this. So these are the spectral form factor that we evaluated. If I look more closely, there's a K equals 1 saddle contributes to comes from these are the yellow lines. So K equals 1 contribute here and here. Right. So this part comes from the K equals 1 saddle, and the K equals 2, the green saddle contributes to this, and K equals 3 saddle contributes to this. So if I only had K equals 1 saddle, namely that explains black hole, it simply decays here and it doesn't come back. Well, it eventually comes back after you wait for a long time, but this is a kind of artifact of the index because it's actually periodic. So the physically more relevant regime will be half of this region. So if I only take K equals 1, then it just drops to 0 and does not come back. But this higher K saddle accounts for this late time behavior and prevents it from decaying to 0.
So what was K? Sorry.
So K is the late label, some labeling of the large N saddle. And typically we kind of ignore this because this is super small. I mean, if K equals 1 contributes like e to the s, then the K saddle contributes e to the s minus over K. So this is extremely small compared to that. So normally it makes perfect sense to ignore this, right? But what actually happens is that if you compute the spectrum, yes?
말했던 오비 폴딩 블랙 different from the
Yeah, I'll get to that. So yeah, so this K greater than 1 saddle, the holographic interpretation of that is that this so these people have identified that as a quote unquote orbifolded space-time black hole. This is in the now have to go to Euclidean signature. And the Euclidean the solution to the black hole in ADS5 cross S5, and you take the orbifold of the entire space-time, including the time direction. And they argue that they account for, well, it definitely, if that's a valid solution in classical gravity, then that's going to explain this factor.
또 이제 이제 다소 불려라지 오렌자 세판
No, that, very good point. Unfortunately, their solution doesn't seem to have a good Lorentzian description. So it's more like a, probably more like a space-time instant lens, but I'm not so sure. Yeah, but at least there is some classical supergravity configuration that gives you soft dominant factors. Which is great. This didn't have anything exotic like wormhole, nor ensemble average. You just need to go non-perturbatively. Well, in the previous example of J2 gravity, they were actually all Euclidean wormholes. Yes. Here, there's no wormhole. There's no wormhole here. No wormhole. That's the hallmark of this computation. So we don't really need wormhole to explain the spectral form factor.
Actually, I'm not sure, but it looks like it's somewhat official because actually I think the first kind of the decreasing how can you say that it is largely depending on the microcanonical value of the delta, right?
Mhm.
So because of that, I think such kinds of decreasing the phenomena largely depending on the delta, right?
Yeah, that is right. Yeah, but that's not really artificial. I want to put delta large enough so that it decays fast enough so that I can see the feature. I mean, if delta, I mean, nothing's wrong with these choice, right? So whatever value I choose, it should be consistent with quantum mechanics, meaning that spectral form factor should not decay to zero at any time. And if I didn't include this orbifolded black hole solutions in the gravity, that's not going to explain this finite spectral form factor.
So you're saying the artificial part is to make the decay happen, but then you see non-decaying phase at some point.
Right, at some finite time. So let me give you one more. Yeah, so my claim is that at least part of, not sure whether full information is recovered, but at least in this context, there's no apparent paradox of information loss. And that information is restored not by the ensemble averaging or wormholes, but by including this orbifolded black hole.
Your space-time is, I mean, each orbifold is labeled by K.
Mhm.
And it looks like you need different Ks.
Yes, I have to sum over Ks.
So it's your ensemble or orbifold. No,
No, it's not ensemble, but this is just a different saddle point of the Euclidean path.
your space-time is
Space-time is just fixed to be just
without orbifolds.
so. Yeah, but this is a solution to the same equation of motion with the same boundary condition. So in that sense, it's totally fine. I'm not like, artificially adding like new degrees of freedom here. So there's I can do a little more. So this 2 pi periodicity was kind of had some nuance. So I just didn't like that. So I can artificially break that periodicity by taking these 2 chemical potentials to be different, especially they differ by some irrational numbers. Then this is what you get. So with some hard work by Sanjin, the computation looked like this. So there's no apparent periodicity. I guess like if you compute this for a very long time, that you eventually come back. But at least for this region, my time can be extended by quite a bit. So we see that this thing doesn't decrease to zero, and if I take some kind of average, then it looks like it behaves something like a ramp. Because like yeah, it's not exactly linear ramp, but once you take the time average, then it goes up. So it's tempting for us to interpret this as an analog of ramp, but without without wormhole geometry. Okay, well, see that's kind of success, but it leaves out some other questions. That is, we don't really see the plateau. I think this problem is not still solved in the context of JT gravity. It's not solved in JT gravity either. But just we would like to do some more experiment. One thing that we did is that we broke the periodicity of index by choosing these two omegas to be irrational. But there's something peculiar about n equals 4 super Yang-Mills, because n equals 4 super Yang-Mills, all the R charges are integral quantized. And if I break supersymmetry to say minimal, n equals 1, then these R charges are not necessarily quantized to be integer. So we may actually have some better feature. So that's what we kind of want you to do. So so that we actually generalize this parallelogram ansatz to n equals 1. And another thing that we would like to do is that, okay, can we actually find like space-time wormhole-like behavior by actually constructing the ensemble average of supersymmetric systems. Say in ADS-CFT, there are lots of examples with a similar geometry. The n equals 1 CFT, for example, that is dual to ADS5 cross some Sasaki-Einstein manifold. And one thing that might be interesting to try is that take the average of theories among different internal geometry in different YPQs, okay, while keeping the gravitational constant fixed. So we did this kind of experiment, and that this is what we have found. So these curves with different colors represent different theories, or that correspond to different Sasaki-Einstein manifold. And this is the graph after taking some average over that different theories. Unfortunately, it doesn't look particularly better than n equals 4. That is our current tentative conclusion. Actually, so my student actually told me that there's actually subtle error in this computation, so we shouldn't really take this plot seriously. But it seems that individual ones have different features. So I was hoping that this will somehow magically create a plateau ramp structure. Unfortunately, it doesn't look like showing us a ramp. So it's still mysterious whether this ensemble average and Euclidean wormhole can emerge by taking this ensemble average of supersymmetric index. So so that's that I'm currently investigating. Okay, so since time's up, let me summarize. So spectral form factor at late time should not vanish for a quantum system with a discrete energy spectrum. However, semi-classical gravity seems to suggest that it should vanish at late time, and that's a one formulation of the information loss. And I have defined the version, some twisted version of the spectral form factor that I call a supersymmetric SFF, and that seems to share a similar property that it seems to vanish semi-classically. Yeah, in the leading order, but there's a subleading contribution of this index that keeps the spectral form factor from decaying. So these saddles are subdominant at early time. It's extremely subdominant, but it becomes dominant at late time. And this is actually seems to be a common feature in many of the recent developments, like such as computation of the page curve and also this spectral form factor. So there are the recovery of information comes from some non-perturbatively self-dominant dominant saddle point. So from some Euclidean path integral approach. So in both of this page curve computation, the wormhole or replica wormhole played a dominant role, but it seems to be negligible at early time, but it actually becomes significant at late time. And noticing that was a source of the success. In this computation, we didn't have to involve ensemble average or wormhole. So there's no factorization problem of the Z and Z bar. So this is a big headache for in the JT gravity business, but by construction, we don't have that. So some of the future direction is that, so I think you mentioned it. So the BPS sector is actually not chaotic. It's quite close to integral, really. But meaning that it's a uniform spectrum of operators. It has some same like this same level spacing. But still, do we have something like the chaotic quantum chaos in the BPS sector? I mean, the reason to ask this is that it's kind of believed that black hole is the most chaotic system in certain sense. So since even in the BPS sector, it captures enough number of microstates and many interesting aspects, can we also see some analog chaos, quantum chaos in the BPS sector? I don't really know, but it would be great. And also more precise understanding of this, our computation is desirable because we don't really know whether this ramp has the correct behavior that is predicted by this Gaussian unitary ensemble for the ordinary chaotic system. So I'm not so sure about that. We have only shown that it does not decay to zero, but actually that's not enough. So we got to investigate this further. And also I showed you this plateau problem that I'm currently investigating. And well, and also it'll be desirable to repeat something similar in other dimensions, but other dimension is technically much harder. So that seems to be one interesting direction to pursue. And that's all. Thank you very much for your attention.
There's questions?
Yeah, I have some question. Do you hear me?
Yes.
Yes.
Okay. Seems that you just calculate from the Yang-Mills part, right?
Yes.
And
Yes.
then you mentioned some saddles, large and saddles with a capital K equal to 1, etc., saying that capital K equal to 1 correspond to the black hole configuration.
Yes.
Could you explain why it corresponds to the black hole configuration?
Okay. So there's a slide that I skipped. That is, so if you use this formula, so if I use the K equals 1 result for the partition function and plug that into the Legendre transformation, then you actually recover the black hole entropy. So this is enough to account for the black hole entropy.
Can you do similar thing for the graviton case that is dominant in the low temperature case?
Yes. So at low temperature, this is not the dominant saddle. So I have explained this K saddles, but there's actually another saddle that is sometimes called as a confining saddle. That is a uniform distribution eigenvalues, and that gives you O1 free energy, and that describes the say graviton gas phase. So
I
there's
see. So it doesn't,
there are other
so it doesn't
competing
appear as a K in the K parameter as a
that doesn't have K parameter.
And the final thing is that you also use the how saying there is a kind of some time, let's say.
Yes.
So what is the meaning of tau in terms of the gravity language rather than Yang-Mills? So what does it correspond to, that parameter?
Oh, very interesting question. Well, in short, I don't really know. That appears as a complexification of the chemical potential. And actually this chemical potential can be so the complexified chemical potential also appears in the gravitational computation. Actually, I'm not really an expert on that subject. Maybe Junho knows better. But yeah.
Okay.
So yeah, I don't know for sure. It's at the moment, this is just a auxiliary parameter that mimics the role of time in this particular context to illustrate a version of this spectral form factor problem. It's actually, it would be great to have more direct physical interpretation of this tau, but I'm not aware of that at the moment.
The resolution of this information loss problem in 2D by wormhole is, to my understanding, generalization to higher dimension is always tricky, right? Considering wormholes in 3 or higher dimension is tricky. So maybe now this was done in ADS5 and CFP4 context. So do you expect that this kind of analysis can be applied to other dimensions, like going back to ADS2 CFP1 or ADS4 CFP3 and study the similar supersymmetric index and introduce this microcanonical SFF and investigate the behavior? Because I think in this case, the existence of multiple saddles are crucial to behavior. Right now, I cannot think of some examples in different dimensions where I observe those many saddles to the larger limit. So that's why I asked you this question. I mean, if it can be generalized to other dimensions, it's great, but right now it's not.
Yeah, so this particular large N saddle crucially depends on 4D for this four-dimensional space-time and the particular form of this elliptic gamma function and its SL3Z property. So it's not clear whether that's easily generalizable in other dimensions, but currently my guess is that there's probably more saddles in three-dimensional index at large N that's not discovered. So that's my current expectation. I may be wrong.
So regarding this, the successful reproduction of area formula starting from index partition function, so that basically implies that this graded degeneracy equal is more or less of same order as the real true degeneracy.
Seems so. So
Otherwise, it shouldn't work.
right. So probably in the sub-leading order, things will deviate. But the most dominant part agrees. I think there is kind of a argument by maybe Ashok Sen about this phenomena that like the index actually captures enough microstates for certain BPS black hole. I don't really know, but
yeah, I think there was some argument about the symmetrical flat black holes by Sen
right
around the time. But to my understanding, no convincing argument for a symmetrical ADS black.
Right. So there might be some. So it'll be nice to come up with some argument along that line. So far this is all empirical. And every time we try, we're quite successful. And I don't really understand why. So there are quite a few technical things that I didn't discuss here. didn't discuss today, like it involves like certain complexification of chemical potentials, and that complexification is actually really crucial in getting the correct entropy. But honestly, I don't have a like firm understanding why, at least from the field theory perspective, why that complexification gives you the optimal counting, like of the microstates.
Could you say more about quantum chaos in this sector?
Unfortunately, I don't have anything to say about quantum chaos in the EPS sector. It's something just very speculative.
Do you have any mind picture from the world perspective?
Oh.
From the world perspective, BPS graph seems to be very, very stable.
Right,
So it is very, very strange to me. What happens in that case from the quantum chaos?
Right. So one thing that's probably related to what Ingyu is working on, I guess, is that there's one related question is that what is the actual shape of the black hole microstates from the dual CFT perspective? I mean, here we have just computed the number of degeneracy, just counted the number of states, but in terms of field theory operators, we know that, like, say, various operator in the boundary CFT maps to, say, variety of particles. We roughly know how it works, but the black hole has huge degeneracy, and it's not so easy to identify the individual microstates of black hole in terms of field theory variable. And one thing that would be interesting to see is that that particular black hole operator might have some notion of complexity. That it's quite distinct from the usual, say, graviton microstate, graviton states. So there's something quite there's some measure to distinguish the black hole microstate versus like usual, say, graviton or particle states. So in that sense, maybe there is some analog of chaos or complexity that there should be some complex BPS operator that somehow show the nature of black hole. That's what I like to see. But you're completely right. The BPS black hole is just stable. BPS states, they don't talk to each other, right? So it's not clear how to define this notion of chaos. So that's the question. Is there something like that?
So actually you derive the area load and CFT side and zero temperature. So how to match, I mean, how to get the entropy in the bulk side in the T equals 0 case?
Oh, this is actually supersymmetric black hole. So it has a finite entropy even at zero temperature. So the entire gravity computation is done at zero temperature.
How to get the area load in gravitational sector?
Oh, in the gravitational. Well, I mean, yeah, here this is so on the gravitational side, what you evaluate, you have a metric, the actual BPS black hole solution, and you can compute its area in terms of these various charges. Since it's supersymmetric, it's extremal. So the mass is given in terms of other charges and angular momentum, and the area takes this particular form. So actually, this identity is gravitational computation, and the first identity is a field theory.
Right hand side is just so derivation or just
this is actual computation for the supergravity. Yeah. Here I have to actually say replace n squared by, say, 1/g Newton, for example. So yeah, by correctly mapping parameters, then
I mean,
areas, just keep.
non-extremal case, actually, the area law can be derived from first law. Where in the extremal case, first law does not vary. It's not vary.
Yeah, right. So here it's simply evaluating the area.
Just the area.
Yes. So this is it's just evaluated area. And this is just in a sense there's no particular meaning here because in the gravitational computation doesn't tell you whether this is entropy, but field theory computation tells that it is.
Other questions? Okay, so if there is no question, let's take again. So